So, yeah, the other day we looked at some color spectrums, right, from different gases, and so what we were looking at was an absorption spectrum, the colors from like the missing areas. If we looked at just those, that would be considered the emission spectrum. Okay, and so let's talk about what's happening when you're seeing that. So it's called electron transition. It's basically when an electron that is in a higher state of energy drops down to a lower state of energy. Okay. So the orbitals that go around the nucleus, right? Those orbitals start out at 1, 2, 3, 4, etc. Electrons can jump from one shell to another shell, right? And so when it does that, it absorbs energy. When it drops back down, it releases that energy. And it releases that energy in the form of a photon. A photon is a quantum we call it a packet of electromagnetic energy. Another word for it would be light, right? It's light. And so we learned before that light was a wave. Well, now we're learning that light is a particle, because remember, photons are some of those exchange particles. And so photons are particles, and that's what's causing the light. So, for example, in hydrogen, if the electron jumps up to the 7th energy level and then falls back to the 4th, you're going to get like a reddish color light. If it jumps up to the 7th and comes down to the 3rd, you're going to get like bluish color, right? And then so how do we know what those colors are? The other thing that you need to know is that these transitions aren't gradual. They're lightning fast. Okay. When it drops from one level to another, it's instantaneous. Okay. And then the transitions are usually drawn using an energy level diagram, which is what this is. Okay. The absorption or emission, right? The how do we know like what color it is or what type of light it is? The amount of energy in the photon determines the frequency or the type of light. Okay. And that follows the this is basically Planck's equation. So we have energy, light energy, is equal to Planck's constant, right? That's just a number that Planck found. And then times the frequency of the light, right? And so Planck's constant is 6.63 times 10 to the negative 34 joule seconds. Okay. And then the frequency is in per seconds. Okay. So if you think about it, we did learn that the speed of light is equal to the frequency of the light times the wavelength of the light, right? Of the wave. If we translate that into here, we end up with the energy is Planck's constant times the speed of light divided by the wavelength of the light. Okay. And yeah. Okay. And so if you're looking at like the different wavelengths, right? The longer wavelengths are in the radio frequency or the microwave frequency. And then you get into the infrared. As we get smaller and smaller and smaller, we go through the visible light, which are the different colors. So each color has a different frequency or different wavelength. Then you get into the ultraviolet and the X-ray and the gamma ray. Okay, so visible is what we can see with our eye. Okay, so let's look at an example. If the example is how much energy does a photon with a wavelength of 827 nanometers possess? And remember, nanometers is times 10 to the negative 9. Okay, so we're going to say that E is equal to H times the frequency. Okay, remember that we could also say that it's h, Planck's constant, times the speed of light divided by the wavelength. So we're given the wavelength, so we're going to use that second half. So h is 6.63 times 10 to the negative 34. C is 3 times 10 to the 8th. And then our wavelength is 827 times 10 to the negative 9. If we do that work in our calculator, we'll end up with 2.41 times 10 to the negative 19 joules. We then need to change that into electron volts, right? And so to do that, we're going to divide, by 1.6 times 10 to the negative 19, right? There are 1.6 times 10 to the negative 19 electron volts in 1 joule. Okay? When we do that, we get 1.51 electron volts. Okay? Here's another example. An atom of hydrogen has an electron in its excited state at n equals 4. The electron spontaneously drops to n equal 1, emitting a photon as it does so. Calculate the energy of this photon in electron volts. So it's starting at 4 and it's dropping to 1, right? So our energy is going to be the difference between where we started and where we ended and where we started, right? So it's the ending energy minus the beginning energy. Okay? So in our table, now each element will have a different table because they have different numbers. But in this case, our beginning is negative 0.85 and our ending is negative 13.58. Put them together. Remember a negative and a negative is a positive. So we end up with 12.75 electron volts. Okay, that's what the energy was measured in. Okay, convert the energy into joules. In this case, we're going to multiply by the 1.6 times 10 to the negative 19 to get the joules. So we end up with 2.04 times 10 to the negative 18 joules. And then C asks us to determine the frequency of this photon. Okay, so the frequency is then the energy divided by Planck's constant. So we end up with 3 times 10 to the 15th. And that would be meters. Okay, and then the last one says use an electromagnetic spectrum chart to determine the photon type. So if you look on an electromagnetic spectrum chart, 3.08 times 10 to the 15th would put you in the ultraviolet zone. Okay, so the next step you want to do is some practice. You need a lot of practice in this. Okay, so good luck.